So thanks for the introduction. My name is Kaiyuan Zhang, a PhD student from University of Washington. And today I will talk about automated verification of customizable middlebox properties. So software middleboxes, such as NAT or firewall, are ubiquitous, and they are playing a critical role in modern computer networks. Their correctness will have a huge impact on the reliability, performance, and security of our internet. And of course, bugs that happen in these systems will always cause serious consequences. Yet unfortunately, these bugs still exist in modern middlebox implementations. So our goal in this project is we want to be able to use formal methods to provide a stronger correctness guarantee of middlebox implementations. Ideally, we'd like to verify existing middlebox implementations, such as the click implementations written in C++. On the other hand, we also want to be able to verify a rich set of middlebox properties, such as the connection persistency of a load balancer. Ideally, we want these properties to be directly extracted or translated from existing RC documentations. Therefore, we could directly use these widely accepted properties as a correctness criteria. There has been a lot of recent works focusing on how to use formal methods to provide a stronger guarantee for middlebox implementations. For example, the Software Data Plane Verification project runs model checking and symbolic execution on click implementation and is being able to detect general safety problems such as unsafe memory operations or infinite loops. On the other hand, VigNet and its more generalized successor, Vigor, uses a combination of symbolic execution and manual theorem proving. And it's being able to prove that the middlebox implementation have the same behavior against a pseudocode style specification. However, none of these previous works do satisfy both of the requirements. Either they cannot be used on verifying middlebox-specific properties, or they cannot work with existing code base. So our approach in this project is we want to use the existing push-button verification approach for software verification and enhance it with middlebox-specific knowledges to make it work with existing middlebox code base. On the other hand, we also provide a set of high-level programming specification language. Therefore, developers could use this interface to specify middlebox-specific properties. So before I dig into the detail of how exactly we perform these two approaches, let me give you a quick introduction of the push-button verification approach. So in general, the push-button verification approach takes the implementation of the software and runs a symbolic execution on top of it. From the symbolic execution, a SMT formula is extracted, where the formula represents all the possible behaviors of the software implementation. On the other hand, a specification is also given by a developer. Basically, the specification is the SMT encoding of the application's property. Both the specification and the SMT formula extracted from the implementation using symbolic execution is then sent to a SMT solver, where the solver will either prove that the implementation and the specification have the same behavior, or it will give you a counterexample where the implementation violates the specification. One major benefit of this push-button approach is that there is no need to write any manual proofs, and this approach has been successfully applied on file system, operating system, and other system softwares. So in order to apply this push-button approach to existing middlebox code, there will be two challenges. The first one is that how do we actually extract a SMT formula using symbolic execution from existing middlebox code base? The other one is how do we actually use the SMT to encode the high-level middlebox properties? So in the rest of this talk, I will first share the result of an empirical study we did on the feasibility of running symbolic execution on click implementations. We showed that using middlebox-specific knowledges and some program modifications, we could be able to achieve a 66% coverage of click configurations. After that, I'll show you the design of our Gravel framework, which contains a set of programming interface to let the developers specify high-level middlebox properties. And then we provide a set of toolchain so that we could Gravel could verify click middleboxes using a two-step verification approach. Using the Gravel framework, we have verified 5 example middleboxes, and we show that using the Gravel framework, the middlebox properties could be easy to verify, and there's no significant impact on the performance. So if we simply run a baseline symbolic executor over the click elements and its configurations, we find that only 16% of the configuration could be supported by the baseline symbolic executor. So why is this happening? After taking a closer look at all those configurations and elements that could not be symbolically executed, we found there are two major factors that stop the symbolic execution from running on these elements. The first one is a false unbounded loop. It's a false unbounded loop because at the runtime, these loops will actually manage to finish executing, but during the symbolic execution, the symbolic executor just do not have enough information to know where the loop will stop. Therefore, it will keep unrolling the loop forever. The other major factor that stops the symbolic execution is the existence of symbolic pointers. The symbolic executor will need to figure out where this pointer is pointing to, but however, since the pointer is a symbolic pointer, it cannot conclude where this pointer is pointing to, therefore it will just abort the execution. So having pinpointed these two major factors that stop the symbolic execution from running on existing Middlebox code base, we propose 5 different kinds of optimizations. Note that for all these 5 optimizations, the first 3 of them does not require any developers interfere, so it can run automatically. The last 2, however, require some slight code modifications or some annotations from developers. With the help of all these 5 optimizations, we'll be able to achieve a 66% coverage of click element configurations. So the first 2 optimizations we're going to perform here is we can concretize the loop and pointer bounds. So we found that a lot of cases, the symbolic executor cannot figure out the actual bound of the loop because it lacks the middlebox-specific or packet handling specific knowledges. As a concrete example, the size of a packet header field is always bounded. For example, the TCP headers option field, its size is always bounded. But however, if the symbolic executor does not have this knowledge, it cannot know where to stop the loop unrolling. Therefore, we just simply give this knowledge to the symbolic executor, let the executor know that where you should stop unrolling the loop. And therefore, the symbolic execution could be able to finish. The second one is find that in lots of cases, the pointers itself in the click elements, these pointers are immutable, which means that during the symbolic execution, it will always point you to the same object, which is not changed. Therefore, we could use a static analysis to figure out whether this pointer is going to be modified or not. If it's not going to be modified, we just skip the reasoning of the symbolic pointer analysis. We could just treat it as a concrete pointer. Therefore, the symbolic executor will know which object this pointer is pointing to, and therefore the symbolic execution could be able to finish. Another optimization we're going to perform here is based on the observation that we found most of the pointer operations that stop the symbolic execution from running come from the implementation of those container data structures, such as hash set, vector, or hash map. However, we found that all of these container data structures could be modeled using the uninterpreted function theory in SMT. Therefore, instead of running the symbolic execution on the actual implementation of those data structures, we could just replace it with the abstract SMT model of it. Therefore, we could be able to finish the symbolic execution over these data structures. And we could take a step further along this path. For those data structures that does not have a corresponding SMT model, we could rewrite the implementation using data structure that have a SMT model of their behavior. As a concrete example, on the left side is a part of code that from the check IP address element. Basically, what this element is doing, it uses array to store a set of bad IP addresses and use a for loop to try to match one address from it. However, because the size of the array is a symbolic value, therefore the upper bound of this for loop is also symbolic. The symbolic executor will have a hard time trying to figure out when this loop will be able to finish. However, since we know that all it has to do is to trying to match address in this array, we could replace it with the hash set implementation. Because hash set have a corresponding SMT model, during the symbolic execution, the code on the right side could be able to finish executing. The last optimization I'm going to talk about here is we can use state concretization. We could do concretization on the read-only state. We find out for the read-only state, where the value of the state does not change during the execution, we could simply use the concrete value of the state instead of a symbolic value. A concrete example of this will be the IP classifier element. What this element do is it uses a finite state machine for packet classification. So if we all use symbolic rules for the state machine transition, then the symbolic executor could not finish the execution because all the state transition rule will be symbolic. Therefore, but since we have this observation that the state transition rules in this element is never got written during the packet processing time, we could just simply extract a concrete value of these state transition rules during the initialization phase. And after that, we could run the symbolic execution using these concrete values. Therefore, the symbolic execution could be able to finish executing. So after applying all of these optimizations, we could be able to achieve a 66% coverage over all the click configuration, which show that it is possible with the use of middlebox-specific knowledges to make symbolic execution feasible on click implementations. So now let's talk about the design of our Gravel framework. So one major part of the Gravel framework is a set of programming interfaces to let developers specify high-level middlebox properties. The idea of this high-level interface is we want developers to write the specification from an external perspective, which means that we want developers to hide low-level implementation details, such as what kind of data structures is actually being used in the middlebox, and focusing more on the external observable behavior of the middlebox. So in this case, using this API, the developer will need to model the middlebox behavior as on a trace of events. So let me give you a concrete example. So let's consider the connection persistence property of a load balancer. Basically, what it says is that if we see at any time that a load balancer forwards a TCP packet to some backend B, then subsequent packets from the same flow should all go to the same backend B within this time window. In order to verify this, we will need to use induction to break down this property into 3 cases. One of them is the base case. Basically, it's that after we see a TCP packet is being processed by the middlebox and is forwarded to some backend B, then the subsequent state immediately after handling the packet should also forward packets from the same flow to the same backend server. And then we also need to have 2 inductive cases, basically show that the packet forwarding behavior is not changing when the middlebox is handling, say, a time event or other packets. So the first inductive case will say that if we're handling a timer event and the time is before T+ window, which is the deadline of the flow expiration, the packet forwarding behavior should not be changed. And the second inductive case will be that handling a packet from different TCP flow does not affect the packet forwarding behavior. So all of these cases can be formalized using a few lines of Python code using Gravel's high-level specification interface. Here is the example of the inductive case 2. Basically, what this code do is it first invokes some calls to create symbolic packet and symbolic states of the middlebox. Then it uses a handle packet call to compute a symbolic state after handling a packet from a different flow. And then after that, we generate a verification target. Basically, we ask this SMT solver to verify that the packet forwarding behavior is persistent before and after you're handling a packet from a different flow. So after having this high-level specification languages to write down the high-level properties of middleboxes and have the symbolic execution to be able to extract SMT formula from the click implementation, the Gravel verification framework will also need to take 2 other inputs. The first one is a element-level specification. Basically, this element-level specification is a state machine representation of the element behavior. It contains a set of states that are going to be used by the element when processing packets, and a set of state transition functions, such as the packet handler. Another input we'll need to take is the click configuration, which is a directed graph that connects all the click elements together to form a complete middlebox. The verification of Gravel is performed in 2 steps. The first step, it takes the click implementation and runs symbolic execution on it to extract an SMT representation and compare it against the element level specification. Then the element level verifier will be able to verify that the implementation and the element level specification have the exact same behavior. After that, it will take the element level specification and using the click configuration to compose all the state transition functions of each of the element to produce a global state transition of the function of the entire middlebox. And this is then compared against the high-level middlebox property to show that these properties will always be satisfied on the global state transition function of the middlebox. So why we are doing this two-step verification approach? There are two major benefits. The first one is because the element level specification are always simpler than the SMT formula we extracted from the implementation itself. Therefore, it makes it easier for the SMT solver to give us a result. And the second benefit is because that the element level verification is performed independently from each other. Therefore, the verification result of a single element could always be reused across different middlebox verifications. So after having this Gravel framework, we then show that we could use this framework to verify 5 example middleboxes: a NAT, a load balancer, a firewall, a transparent proxy, and a learning switch. So for all the 5 middleboxes, we've been successfully verified a total of 11 different middlebox properties. Note that these properties are actually translated from RFC documentation, which is a good indicator to show that Gravel's specification interface is expressive enough for developers to specify interesting middlebox properties. We also try to see whether these verification techniques can actually prevent bugs. So below is a table that shows a list of bugs we find in bug reports of other middlebox implementations. We manually inspect each one of them to see if our verified version of the middlebox could prevent this bug from happening. We found that besides one bug, which regarding to the initialization phase of the middlebox, which currently Gravel does not try to verify, and 2 of the bugs regarding to a performance property where the Gravel currently does not have a specification for it, all the other bugs could be prevented by the verification technique. Another interesting finding we found is the MazuNet implementation from the click does not satisfy the endpoint independent mapping and hairpinning property that are required for a NAT to support peer-to-peer communication. Regarding to the verification effort, the NAT itself took us about 5 days to both specify and to verify, and all the other middleboxes takes us less than 1 day to finish the verification process. And during the process, we find that less than 10% of code changes are required, and the solver itself is relatively fast to run. It takes less than 2 minutes to verify all the properties of a single middlebox. As I just mentioned earlier, because we only need to introduce less than 10% of code changes, the performance of the verified version compared to the unverified version does not introduce much of a performance overhead. So to sum up, we show that by introducing domain-specific knowledges and having this domain-specific optimization, we could be able to make symbolic execution feasible for running on existing middlebox implementations. And then we show that we designed the Gravel framework, which contains a set of program-friendly specification language for developers to specify middlebox properties, and using this two-step verification approach to make it possible to verify existing middlebox code base. We have applied this Gravel framework for 5 middleboxes, and it shows that we could be able to express and verify RFC properties with minimal programming and verification costs without introducing much more performance overhead. Thanks, and I'll take some questions.
Hello, Zhuo from Northeastern. So it's nice talk, nice topic. So recent years there has been other NF framework other than Click. There's like NetVM and there's NetBricks, etc. Can you quickly comment on how the the verification work here can get applied to those frameworks?
So the problem is like this analysis is done on Click itself. So because like symbolic execution can be tricky to be enabled on these systems. So I cannot guarantee that this will always work on other platforms, but I think 2 very high-level observations we found is for performance reasons, middlebox code or packet processing code is often written in a way that the step the operations performed on a single packet is always finite and small. So if this
the background is
yeah. So because of that, I would say that it is highly likely that symbolic execution would also work with modifications, of course, on these other platforms. But I cannot say for sure before actually seeing this code or trying by myself.
One more quick question.
Yeah.
Hi, Jeremy Epstein, National Science Foundation. Interesting stuff. I'm curious, you undoubtedly found problems in the verification process. What sort of problems did you find in the middleboxes?
Can you repeat the question again?
So presumably the verification process uncovered things that were wrong.
Yeah.
So what sort of things did you find that were wrong?
So in the process of verifying these middleboxes in Click, we found that the net implementation in Click does not satisfy the two of the properties that we translated from the RFC documentations. So these properties are required to support peer-to-peer communication according to the RFC documentation. So this is one example of what we found.
Were there any problems you found that were completely unexpected?
Actually, these two properties, when we try to verify these, we didn't expect this to happen. But other than that, I think the other middleboxes seems to be okay. We didn't find any interesting bugs in these middleboxes.
Great. Let's thank our speaker.